Here I'm going to define what is meant by a boundary value problem. So a boundary value problem is similar to an initial value problem with the exception that we have the solution at both ends of the domain. So here we have a common type of boundary value problem, which is a second order ODE. So you can see we've got y double dash equals f of ty. So this is a second order ODE over the domain t min to t max. We have the initial solution as with an initial value problem. So the solution at t min is equal to y0. We've also got another solution, and that's at t max is equal to some value of yn. Okay, so a boundary value problem is so called because we know what the solution is at the boundaries of the domain. Now, not all boundary value problems have a solution, and some boundary value problems have more than one solution. So we're just going to consider an example here. So here I've got a first order ODE, okay, and the general solution to this is easily found by integration. It's some coefficient c1 times cos of t plus another coefficient c2 times sine of t. So we're going to consider some different instances of the boundary values. Okay, so we're going to say if we let our initial value be 0 and our upper boundary, which is where t is pi over 6, is equal to 1, okay, well for each of these cases I can use these to calculate what c1 and c2 would be. Okay, so for the lower bound we've got a value of 0, so when t is 0, so cos of 0 is 1, sine of 0 is 0, so therefore c1 must be equal to 0. And on the upper bound case we have a value of 1 at the upper bound, and t is pi over 6. Okay, so cos of pi over 6 is root 3 over 2, sine of pi over 6 is 1/2. So since we already know that c1 is 0, okay, so c2 must be equal to 2. So we have the unique solution, y equals 0 cos t plus 2 sine t. Okay, well what about another case? Okay, so here we still got the initial value equals 0, but now we've got an upper bound of t equals pi, and that solution is 0. So again, for the lower bound we have c1 equals 0. For the upper bound, well, cos of pi is -1, sine of pi is 0, so we've got 0 equals minus c1. Okay, so c1 has to be 0, but we have no information about what the value of c2 is, so c2 can take on any value, so this boundary value problem has an infinite number of solutions. And for a third case, we've still got the same same initial value, but our upper bound is at t equals 2 pi, and that's got a value of 1. So if we do the same, c1 is still 0, but here cos of 2 pi is 1, sine of 2 pi is 0, so we've also got 1 equals c1. So c1 cannot equal both 0 and 1, so that's a contradiction. So this boundary value problem does not have a solution. Okay, we can extend that to a theorem. Okay, so for a second order linear ODE, we can write it in this form. So we have some function p, which is our coefficient of y dash, another function q, which is a coefficient of y, plus another function which is a constant. So if p, q and r are all continuous on our domain, so continuous essentially means if we sketch the graph of these functions, we wouldn't have a split in the graph. Okay, so you can graph it using one smooth continuous line. So that's the first criteria. The second criteria is whether the coefficient of y is at positive for all values of t in the range. So if these two criteria are satisfied, we have a unique solution to the boundary value problem. So here we have an example 5.1. So we have a second order ODE. So if we compare it to this one up here, we can see that the coefficient of y dash is 0, because we've got no y dashes. The coefficient of y is t cubed plus 5, and the constant, or the constant function rt, is sine t. Okay, so these functions are all continuous on this over the range 0 to 1, and also qt is greater than or equal to 5. Okay, so there are cases where qt would be less than 0, but because we're only interested in our domain, but we can see that qt is always going to be greater than or equal to 5, which is obviously greater than 0. So this boundary value problem has a unique solution.